So today we will talk about waves and oscillations, and this will be an introductory lecture about how the waves are generated and how they are manifestations of various oscillations and how the waves are classified into longitudinal and transverse waves. This is a basic introductory lecture. So we start with the concept of waves. What are waves? So basically, a wave has been defined as a disturbance that travels through a medium or a space. So you can see that when you drop a stone on the surface of a water, you can see that the disturbance travels in the form of circular circles, and these circles represent waves. You can see this is a circle, and the two ends of the circle represents the two maximas, and the diameter of the circle is the wavelength. The points of maximum displacements are called crest, and the center, which is the point of the minimum displacement, is called trough. When we drop a ball into water, what happens? We see this kind of a motion. The ball is coming up, going down, and again coming up. And at the same time, it is also moving on the surface of the water. So basically, this has created a disturbance that is traveling in the form of a wave. If you analyze, this is a wave kind of thing. It is going down, making a trough, coming up, making a crest. So this is kind of a wave that has been excited when we drop a ball on the surface of the water. If we poke a ball, just the ball is there and we disturb it. So there is a motion of this. It starts coming up and going down at the same place. It is not going right and left. It is just coming up and going down at the same. But the disturbance are traveling in the form of the waves. While it is going down, it is giving pressure, and there is a disturbance which is traveling on the surface. Like see here, these are the disturbance. If we take a soft spring, a long and a soft spring, and if we take it away from the position of the equilibrium, and then again back, so the disturbance moves. You can see that the disturbance is moving, and the energy is being transferred. So this disturbance, which was excited by a single push, is called a pulse. And if we keep on repeatedly pushing again and again, we get a repeating disturbance. And this repeating disturbance will look something like this. And then this happens at a more higher pace, then it will be a continuous. So one more thing, we see that the disturbance is moving, but the spring is not moving. The slinky is not moving, only the disturbance has traveled. The disturbance has traveled, then it again back to the normal position. I excited the disturbance, it is traveling, it is coming back to the normal position. The medium has remained as such, only the disturbance traversed. If we take a string, tie it on the wall, move it up and down, what we see? That there's a transverse wave going along. The disturbance created by the hand on the rope is traveling to the support. So that means it is traveling in this direction. And the wave is traveling with a velocity v. The wave disturbance has traveled, but the rope is there. The rope is there, the particles of the medium are there. Because the particle of the medium move away, then the shape of the rope will be distorted. But the shape remains as such. That means the particles of the medium of the string are in the same position as they were before, only the disturbance has traveled. So basically, when the disturbance travels, it carries energy, and the particles of the medium do not move, but only the energy is transferred through the medium. And this is transference takes place through vibrations. Just notice this particle. The wave is coming, the particle is set into oscillation, it moves to and fro, and again comes back to its mean position, again moves to and fro. The disturbance, that pulse is transmitted, and it again comes back. Repeatedly, pulses are coming, and it is transferring those pulses, but is not changing its own place. If these disturbances are progressing in this direction, in the horizontal direction, it is a longitudinal wave. And if it is in the perpendicular direction, it is the transverse wave. We will discuss it later on. These are some quantities that you ought to know. The point of maximum displacement is called the thrust, and the point of minimum displacement is called the trough. And the magnitude or the maximum or the minimum displacement is called the amplitude. The distance between two consecutive crests or troughs is known as the wavelength, and the speed of the part of any periodic wave of frequency is defined as v is equal to lambda f. Lambda is the wavelength, f is the frequency, v is the velocity of the wave. This is the formula. You can see the same thing. Maximum displacement is the amplitude. The time required to travel one wavelength is the time period. And inverse of the time period is the frequency. That is the number of oscillations in unit time. Mathematically, a wave can be described in this form, a cos or a sine, which comprises of a fixed amplitude and an oscillatory part. The amplitude is fixed, although it changes, but at a point it is fixed. This is a cos or sine wave. It consists of two parts, one dependent on space, one other dependent on time. The direction coming with the wave number of the propagation constant k, its value is 2 pi by lambda, and the direction or the position which is coming here, it denotes the direction of propagation. That means that this wave is propagating in the x direction. Omega is the angular frequency and is given by 2 pi f. F is the linear frequency. The time period of in the spring is given as 2 pi under root n upon k, and n is the mass per unit length, and k is the propagation constant. So see this spring, we fold it back and release it. Pull it back to a position x, release, it will come inside to a similar displacement x. We pulled it by a distance x. It will, after release, it will come to its mean position, and again travel further in the opposite direction to the same value x. Such type of motion is called simple harmonic motion. And in this, force is equal to minus kx. That means the force is proportional to the displacement in the opposite direction. Such kind of oscillation is called simple harmonic, where the force is proportional to the displacement directed in the opposite direction. If the spring is hung vertically, they are only vertical oscillations, and the force is equal to the gravitation. The energy in this simple harmonic motion, we have two energies, the potential energy of the spring, which is half kx square, k is the spring constant, and x is the displacement. So total mechanical energy is the kinetic energy, half mv square, and the potential energy. The total mechanical energy is conserved if we assume all the system to be frictionless. At the end points, the kinetic energy is zero, because if we pull this, we hold this. So at that point, we hold the point is at that instant at which it is being holded, it is at rest. So the kinetic energy will be zero, and all the energy will be half potential. Similarly, at the other end, when it comes to rest, it changes its direction. So at the instant of the maximum displacement, it is rest for a moment, and then it will change the direction. At that instant, the kinetic energy will be zero, and the energy will be only potential. The total kinetic energy the total energy is given by this expression, and we can equate it to this energy where A is the amplitude of the wave. The velocity of the wave is given by this expression, which is calculated from the wave equation that we discussed before. This is the displacement. We differentiate and we get the velocity. This is the same velocity. So now let's again come to the same concept. The displacement of a simple harmonic wave can be described by this. We have neglected the space. So it's A sine omega t. This is the simplest form of a simple harmonic wave. Now we differentiate this with respect to time to get the velocity. Again, we will differentiate this with respect to time to get acceleration. And acceleration is proportional to the displacement in the opposite direction. So similarly, the force is also. Now, when the amplitude, if we pull the spring, release it, it will start, the oscillations will start slowing down, and ultimately it will come to rest. So there is an decrease in the amplitude of the wave, and the amplitude, when it comes to rest, the amplitude of the oscillations becomes zero. So this reduction in the amplitude and gradually coming to rest is called damped harmonic motion. When you just see this example, there's a string. A person pushes the string to set into motion. So that means the string comes into oscillation like a pendulum only when this person pushes him, or there is the force which the rider himself jerks. So the oscillations come into practice after the exertion of the force. So these are called force oscillations. And if the frequency of these force oscillations is same as the natural frequency of the oscillations of the body, then it is called resonance. And at resonance, the amplitude becomes a maximum. You just notice this diagram. This is the frequency. And at resonance, the amplitude is suddenly increased. There's a sharp increase at resonance. As I pointed out earlier, there are two kinds of waves, longitudinal and transverse wave. If the disturbance is traveling, vibrations of the medium are oscillating in the perpendicular direction, it's a transverse wave, and if they are oscillating in the same direction as in the as of the propagation of the disturbance, that is called longitudinal wave. So this is a longitudinal wave. The disturbance is also in the direction. So this is a longitudinal. Such a type of wave is used to transfer sound. Sound waves are longitudinal. You see, disturbances propagating in this direction. The particles of the medium are oscillating in to and fro motion. There is no vertical displacement, only the horizontal displacement of the particles. The wave is moving, see, but the particle is not moving. Particle is oscillating only at its place. The wave is moving. If the oscillation move perpendicularly, then it is a transverse wave. The particles are oscillating in the perpendicular direction, the vertical direction. They are not changing their position in the horizontal direction. So such a wave is called a transverse wave. When two waves superimpose, then that process is called interference. And the resultant displacement is the sum of the displacements of the two waves. You can see these are two waves. And at the point where they superimpose, it becomes maximum. So these two superimpose maximum, there is a maximum here. When they minimum superimpose, it's the minima here. So when the maxima superimpose to give a maxima of double the amplitude or the addition of the amplitude, it's called constructive interference. When the minima is superimposed, the amplitude becomes further minimum. It is called destructive interference, which is constructive. And when the minimas interfere, that's the minimum amplitude. So that's a destructive interference. That is for today.